Find the area under the curve over the given interval. So we have a graph of y equals 4x squared. Let's get a nice little visual. This isn't going to be a perfect picture. I have a hard time drawing graphs with this little pen thingy. But 4 over x squared looks, give or take, something like this. Give or take. Now, what it's asking me to do is let's find the area under the curve between -2 and -1. It wants this area right here. Well, what's going to happen, and what I could use, is the integral of this equation is going to give me the area under the curve. I'm going to use -2 and -1 as my limits of integration to help me find this area. So this is going to give me some number, and that number is going to be the area under the curve, between the curve and the x-axis, between -2 and -1. So let's get rid of this mess. Let's start the problem from beginning to end. I need to find the integral of 4x, or rather 4 over x squared dx, where my limits are bottom limit -2 and -1, because my lower limit here is -2 and my upper limit's -1. Let's rewrite this. Let's bring that 4 out if you want to. Let's make this x to the -2 dx. Sloppy, but you'll get it. Let me see, 4 times, let's add 1 over -2 plus 1, x to the -2 plus 1, close that. My limits of integration are still -2, -1, can't ignore those. Can't ignore those. So we got 1 over -2 plus 1, which is 1 over -1, which is -1, and -1 times 4 is -4, x to the -2 plus 1, which is -1. Limits are -1 and -2. And let's just rewrite this out one more time before I use the fundamental theorem of calculus as -4 over x, limits being -1 and -2. So fundamental theorem of calculus says, once I have my integral complete, I rewrite my solution here, -4 over x, but instead of x, I am going to plug in my upper limit first, which is -1, close it, always the minus, rewrite that guy, -4 over x, but instead of x, plug in the lower limit, and do a little bit of math. -4 over -1 is +4, minus sign, -4 over -2 is going to be 2. 4 minus 2 is 2. So that little picture that I gave you, right, where we were focusing on what's happening here, and we had that little chunk, that chunk that's filled in right there has an area of 2, and that's how you find the area under a curve. Find the area between the curves, curve number 1, curve number 2. All right, so this is what I'm going to do. I'm just going to make believe that I know exactly what these curves look like. So that's a parabola. Parabolas usually look like U. This is a parabola. Parabolas usually look like U. Obviously, these aren't perfect, okay? But what I also know is that x equals 1 when graphed is a vertical line, okay, and x equals 3 when graphed is a vertical line, and I care about this shading right here in between these guys. So when you find the area of a curve in general, you take the integral. Now, if you have two curves, you're going to subtract one integral, or one equation minus another equation, integrate that, and then you have the area that you want. Now, the fun part about this is we know what my limits are. My limits are 1 and 3. So my job is to find this mess right here. So let me erase all of this, hit the reset button. Let's go for it. Now I'm going to write out this really big integral, okay, where I have, and you know what, let me put this whole thing in brackets, otherwise it's technically not, sound. 2x squared minus 8x plus 10 minus x squared over 2 minus 2x minus 1, close it, bracket it, dx. Now, if you're wondering, well, which equation is definitely the above one? My job is to find an area. It doesn't really matter which equation you put first, as long as you use common sense. If I do all of this and I get negative 50, that means I did it upside down, and I just changed my answer to positive 50 because you can't have negative 50 as an area. I'm not saying that that's what's going to happen here, but, we'll see. Now, what I do have going on in here, oh, by the way, I can't forget that I have limits, and my limits are 3 and 1. Ooh, 3 and 1. The Trinity. So I have, let me see, this is going to be a mess. Let's write this all out, although I really don't need those parentheses anymore because I'm going to try to simplify parentheses. So I've got 2x squared minus 8x plus 10, distribute this negative, and let me write it out as a better looking fraction. So that would be 1/2 x squared plus 2x plus 1, close the bracket, dx. I think I should be able to squeeze it in here. 3, 1. All right, 2x minus half an x is 3/2 x squared. 3/2 x squared, can't forget that. I have negative 8x, positive 2x, negative 6x. 10 plus 1 is 11, last time I checked, dx. Okay, so let's take the integral of each one. Let's take the integral of each one. I get 3/2, okay, times 1 over 2 plus 1, which is 3. How nice. X to the 2 plus 1, which is 3. Okay, let me put a huge brackets here. Minus 6, 1 over 1 plus 1, which is 2. X to the 1 plus 1, which is 2. Plus 11, and you just attach an x. My limits of integration are going to be 3 and 1. So we get 3/2 times 1/3 is going to be 1/2 x cubed minus 3 x squared plus 11x between 3 and 1. All right, now let's use the fundamental theorem of calculus, which has me writing this whole monster out, plugging in 3, minus sign, write this whole monster out, plugging in 1. So let's do it. So I have 1/2 times x to the third, so 3 to the third, this is going to be awful, minus 3 times 3 to the second power, plus 11 times 3, minus, okay, the exact same thing, but plug in 1, 1/2, 1 to the third, I can handle that one, minus 3 times 1 squared, plus 11 times 1. All right, let's see what I can do in my head. Let's see what I can do in my head. I'm actually going to step to the side and just do all the math on a calculator and then come right back and tell you what the answer is. It's 11. All right, I ran out of room, so if I wanted to, I could have been like, all right, well, 27 over 2 minus 27 plus 33, and then have a big mess. But according to Mr. Calculator, I get 11, and I'm going to trust Mr. Calculator. Mr. Calculator, I'm sorry, or Ms. Calculator is pretty smart. So that's the area between curves. So whatever that black space was, that was right here. It's 11. And again, if I got negative 11, that's just because I had these upside down. I had the wrong order in which I had my lines. Not the end of the world. Just make it positive because you can't have a negative area. All right. Fun. Find the volume of the solid that results when the region enclosed by the curves is revolved around the x-axis. All right, so what you have here is called the washer method. Just go with me here. Pretend that this little blue sliver is going to be spun around, or better yet, pretend that your finger is on this x-axis and you're slowly spinning this around. And when you spin this around, it creates like a kind of like a cone-shaped solid, almost like a bowl without a bottom. All right. Now what you have is a 3D figure created by this thing being spun around. That's what we're dealing with. Okay, this method is called washers. Now, there's another method called discs. It's on my YouTube. Look it up. But the washers method is called the washers method is when you spin it around the x-axis, there's this gap in between the actual curve and the x-axis. If there's no gap, if it's something that's attached to the x-axis, that's when you would use the disc. But this is called the washers because like a washer as a tool, you have that hole in the middle. So we'll have that. The way you do this is you set up an integral, right? You throw pi in front of it. You have an upper limit and you have a lower limit. And a lot of teachers use r to represent one of these. So you're going to have like both of your equations. I'm not going to figure out which equation is which. I'll explain that in a minute. But you're going to have like an upper equation, the equation that belongs on top, okay, of this solid. You're going to call that r sub o. And you're going to square it, and you're going to subtract r sub I, and you're going to square that, close that, dx. Now, again, when you are creating your integral, the r sub o is going to be the top part of the solid or the top part of the area. So this equation right here is going to be my r sub o, and this curve is going to be my r sub I. All right, so let's label what I know now, okay? And there's a few things that we have to do before we can even get started. First thing is I now know that this is going to be, this curve is my r sub I. So the parabola, which is this equation, is my r sub I. This is going to be my r sub o, so let's put that in our back pocket. What we also need is my upper limit and lower limit. Now, it might be obvious here, but what if it wasn't obvious? I have to find what x value this is, which is now called a, and I have to find out what this is b. Now, it looks like 2 and 0, and it probably is 2 and 0, but what if the numbers aren't as friendly? What if the equations aren't as friendly? What do I do then? Well, in order to find the x values that these guys intercept, I have to solve the system of equations. So just like you would do like, a regular system of equations, I'm going to use substitution. It's y equals this and y equals that. So set 2x plus 2 equal to x squared plus 2. Now I'm going to set this equal to 0 by subtracting 2x. Nothing combines over here. If I subtract 2, that makes my life a little bit easier because that all cancels out. And now I'm left with 0 equals x squared minus 2x. Okay, using the zero product property and a little bit of factoring, I get x times x minus 2. Set both of these equal to 0. And one of my limits, this guy is 0, so I guess I was right. And if I were to say x minus 2 equals 0 and add 2 to both sides, 2 would be my other limit. So now what I know is I know that my upper limit is going to be 2. My lower limit is going to be 0. My r sub 0 and r sub I is already set. Now we can get started. So let me erase this whole mess. I'm not going to clear the screen because I want to keep this stuff over here. Okay. All right. I'll probably have to write small because I have a feeling this is going to be a mess. So I've got 2 and 0. I've got r sub o, which I said is going to be my line. So I have 2x plus 2 squared minus x squared plus 2 squared, close it, dx. Okay, before I even think about integrating, I need to do a little bit of simplifying in here. So let me do just that. Okay, perfect square trinomial. So this part becomes 4x squared plus 8x plus 4 minus another perfect square trinomial. There's my phone. X to the 4th plus 4x squared plus 4 blip, blip, dx. Let's combine like terms. Still not even close to being done yet. Not even close. I've got, what's it called? Distributing the negatives. So I have 4. I can drop these parentheses. 4x squared plus 8x plus 4 minus x to the 4th minus 4x squared, which is good news. And you'll see why. And more good news. So I take it all back. This wasn't so bad at all. Minus 4, close it, dx. So you'll cancel out. You'll cancel out. And I'm left with 8x and negative 4x. So I have the integral between 0 and 2 of 8x minus x to the 4th dx. Once I integrate, that pi is just going to live right out there. All right. So I have the integral of 8x is going to be 4x squared. The integral of minus x to the 4th is going to be negative 1/5 x to the 5th. And my limits of integration are 0 and 2. All right, so let's leave this pi out here. Let's leave this pi out here. That pi is just going to exist out there, and I'm going to make sure that I keep it attached to my final answer. I hope I gave myself enough room. Fundamental theorem of calculus time, plug it in. So let's try to do as much in my head as I can. I have that pi there. I'm going to plug in 2. So I'm going to have 4 times 2 squared, which is 4 times 4 is 16, minus 1/5 times 2 to the 5th power, which is 32. So 32 over 5. I'll deal with that when I have to deal with that. Minus pi. 0. Oh, look at that. Look at that. If I plug in 0, I get 0 minus 0, which becomes 0, which makes all that 0. So I'll just completely erase you to make my life a little bit easier. 16 minus 32 over 5. Ugh. I'm going to consult Siri. 16 minus 32 fifths.
The answer is 9.6.
So this final guy is going to be, what the heck? This final guy is going to be 9.6 pi. So yeah, that's the washer method. Very similar to the disk method. Again, this is the washer method because when you spin it around, you get that space in between, unlike the disk. I have a video on that. Go find it. It'll be great for you. Find the volume of the solid that results when the region enclosed by the curves is revolved around the x-axis. All right, so basically what we're doing is we're taking this little circular looking thing right here, and we're pretending that that's like like a piece of paper, like a 3D printer thing, and we're spinning it around. So what's going to happen is this little orb right here is going to spin around and create a 3D orb looking thing. All right. This method is called disks. Now there's another method very, very, very similar called washers that we're not going to use here. Washers is if you kind of have like a space, like when you spin it, you create like a donut or a space in between. It's called washers because just like the tool washers, it has a hole in the middle. Not this. This is called disks because you're going to spin it around and not have any space in between it. Now, what we're going to do is we are going to take the integral of whatever equation this is. So we'll call it r. We're going to take the integral of r, square it. We're going to have a lower limit and an upper limit, and we're going to throw pi in front of it. Now, if you're looking at this and saying, that's kind of like the volume of a cylinder, you're absolutely right. Because what we're doing is we're kind of creating like a continuously changing cylinder, if that makes any sense at all. Okay, so this is the method that we're going to use. Now, we have our r. That's our r. And if you're like, what about y equals 0? Y equals 0 is just a fancy term for the x-axis. Don't worry about it. Don't worry about it at all. Now, what we don't have yet is we don't have our limits of integration. We don't have a and b. So this is what we're going to do. We have to find where our curve, where r crosses the x-axis. In other words, where is negative x squared plus 1 equal to 0? Now, we can look at this and say, well, I think it's kind of obvious what the answer is, but you can never be too sure, ever. So since I'm not too sure, and since these numbers could be not friendly in the future, I'm just going to do it this way anyway. So I'm going to add x squared to both sides, like that. I'm going to square root both sides. Don't forget your plus or negative. And that gives me x is equal to positive or negative 1. So my limits of integration are positive 1 and negative 1. All right, so now I know what I have. I think if I do all of this here, that leaves me with enough room. So let's see if I can pull this off. I have pi times my upper limit, which is going to be positive 1, my lower limit, which is going to be negative 1, my equation, which is going to be negative x squared plus 1, all of that squared dx. Before I can even begin, I need to square that guy. So this is not as simple as squaring both numbers. This is a perfect square trinomial. So this gives me x to the 4th, negative 2x squared, right? And positive 1. Now I integrate. Pi comes along for the ride. This gives me 1/5 x to the 5th. This gives me negative 2/3 x to the 3rd plus x. My limits are negative 1 and 1. All right, so I'm going to now use the fundamental theorem of calculus. I'm starting to get a little nervous that I don't have enough room, but we'll find out. I'll just write small. Fundamental theorem of calculus says rewrite this guy, but replace every x with the other limit. So I have pi. Let's do a little bit of mental math. 1/5, because the numbers aren't that bad. 1/5 times 1 to the 5th is 1, so 1/5 times 1, easy. Minus 2/3. 1 to the 3rd is 1, so minus 2/3 times 1 is minus 2/3, plus x, which is plus 1. Okay, got it. Minus. The second part of fundamental theorem of calculus is write that out again using the lower limit. So I have 1/5 times x to the 5th, which is negative 1/5. Same thing's going to happen here, but that's going to be positive 2/3 minus 1. If you're looking at that, you're like, oh, well, this is the exact same. After I distribute the negative, this is the same as that. That makes sense because these guys are symmetrical perfectly. So I'm not going to lie. I'm just going to quick use Siri and find out what 1/5 minus 2/3 plus 1 is.
It's approximately 0.5333.
So 0.533, I'll leave it like that. That's no problem. 0.5333 pi plus 0.5333 pi is going to end up being 1.0666 pi. And that's the discs method. Fun, 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 fun. Find the volume of the solid that results when the region enclosed by the curves is revolved around the y equals -1 axis. All right. So what this looks like is a washer's problem. And what we're usually used to in a more basic, even though it's difficult version, is you're used to spinning it around the x-axis. Well, this is different. So when it was spinning it around the x-axis and you use the washers, you have your lower limit, you have your upper limit. You throw a pi there. Okay. And when it's washers, you take what you determine to be like the upper curve, which is RO, which this is the case, and we have RI here. What you did back then is you would say RO squared minus RI squared dx. Well, when it was the x-axis, y is 0. So that was fine. But now that we're spinning it around a different axis, we have to change things up a little bit. So let's erase some of this because we are adding another unit when we spin it around. If we were to spin it around the x-axis, no big deal. But now when we spin this around, we have to pretend that this guy is creating like this weird donut-looking shaped thing here. I can't draw. But it kind of creates a bowl where actually you have to believe that there's like a hole in the middle. So we kind of have this weird looking donut-y thing. Okay, but we're adding another unit. So whatever number y is, the best way to probably view this is minus y. Okay, where in this case, y is -1, so it'll become +1, but then you take that, you square it, and then you subtract r sub I, do the same exact thing, square that, close it, dx it. So that's what we're looking at. Now, the other thing that we have to take care of is even though it's kind of obvious, we can never have the benefit of the doubt and say that that's definitely 0 and that's definitely 1. So we need to find out what my upper limit A, or B rather, and my lower limit A is. So I'm going to do that by finding out where these two guys intersect. So we're going to pretend that that's a system of equations, and we can solve that using substitution and say root x plus 1 equals x squared plus 1, bada bing. Let's set this equal to 0. So let's subtract root x. Let's subtract 1. Let's subtract root x. Let's subtract 1. That goes away, and you have 0 equals x squared minus root x. Okay? The way I'm going to handle this is I'm going to use zero product property, and this is going to be strange, but go with me here. I'm going to factor out a root x. By factoring out a root x, I am left with a root x cubed, or x to the 3 halves, minus 1. And we could use the zero product property. Root x is equal to 0. So this factor equals 0. Square both sides. X is still equal to 0. So that gives me that guy. My lower limit is kind of obvious. My upper limit should be 1, but just to be on the safe side. Square root of x cubed minus 1 equals 0. Add 1. Square root of x cubed equals 0. Square and cube root both sides. X is equal to 1. I'm sorry, 1. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. I'm getting too jumpy here. Getting too jumpy. All right, so now what I have is I have my upper limit. I have my lower limit. Time to have some fun. Let's call u 1, let's call u 0, and let's write small. See what happens. Let's get rid of all of u. If you have to, clear that out, clear that out. All right. Pi, integral, upper limit, lower limit, bracket, r sub o I called the square root. So I'll call you r sub o, I'll call you r sub I. So this is going to become r sub o, which I don't know why I did that. R sub o is root x. So I'll write that as x to the 1/2. Makes sense to me. Plus 1 minus -1, so plus 1 again, squared, minus r sub 2, or r sub I, minus r sub I, which is going to be x squared plus 1 minus y, which is negative 1, so plus 1 again, squared, bracket it, dx it. Okay, so let's do a little bit of simplifying. Pi still lives there. I'm far from integrating. So if I were to do that, that becomes x to the 1/2 plus 2 squared minus x squared plus 2 squared dx. Okay, let's do, we've got ourselves two perfect square trinomials that we're going to end up with. So this is going to become x plus 4x to the 1/2 plus 4 minus, this is going to become x to the 4th minus, or rather plus 4x squared plus 4, close it, bracket it, dx it. Okay, let's try to simplify and distribute the negative at the same time. This is going to be interesting. So x isn't going to be touching anything else, so x is just x. Plus 4x to the 1/2, that's not going to be changing anything either, so plus 4x to the 1/2. Plus 4 and minus 4 will cancel out. We've got minus x to the 4th minus 4x squared. That's our integral. There you have it. So I'm going to leave that down there. And I'm going to do the integration up here after I erase everything. This is going to be a mess. However, the nice thing about this problem is since the lower limit's 0, things will go away, and that's going to make our lives a whole lot easier. Okay? All right. Pi still lives out there. The integral of x is 1/2 an x squared. Okay. The integral, this is going to be an interesting one, of 4x to the 1/2. The 4 is going to live there. And then you get 1 over 1/2 plus 1, which is 3/2. So 1 over 3/2, right? And I'm just going to do the math right here and then erase things. 1 over 3/2, when you divide by a fraction, you just get its reciprocal. When you divide 1 by a fraction, you get its reciprocal. So 1 divided by 3/2 is 2/3. And you end up with 8 over 3. X to the 3/2. Okay. Minus 1/5 x to the 5th minus 4/3 x to the 3rd. My limits are 1 and 0. All right. Pi 1/2 x to the 2nd power is now 1 to the 2nd power. So you tell you what, let's make life easier. If we're doing the fundamental theorem of calculus, 1/2 times 1 squared is just 1/2. Let's not overthink it. Plus 8/3 plus 1, or times 1 rather, so plus 8/3 minus 1/5 times 1 minus 4/3 times 1. That guy's done. Minus pi. And I'm going to plug in 0 for all of these. So 0 times stuff, who cares? 0 times stuff, who cares? 0 times stuff, who cares? 0 times, they're all going to become 0. So this ends up being pi times whatever this guy is. I'm just going to let Siri do it. 1/2 plus 8/3 minus 1/5 minus 4/3.
It's approximately 1.6333.
I'll take that. 1.6333 times pi is going to be 1.6333 pi. So that is the volume of a washer bowl thingy spun around an axis that is not the x-axis. Very tricky problem. Tons of fun, though. Use the method of cylindrical shells, or just regular shells, to find the volume of the solid that results when the region enclosed by the curves is revolved about the y-axis. All right. So we've got ourselves this shape-looking thing created by that line, that curve, enclosed off by 0 and 4. And what we're going to do is we're going to rotate this around the y-axis to create some kind of weird 3D top-looking shape that looks like something like that. So as you can see, I'm not a gifted artist, but that's basically what we're getting here. Now, generally speaking, when you use the shells method, all right, when you use the shells method, the way you find the volume is you take the integral where your limits of integration are going to be between a and b, which is created by 0 and 4. So 0 and 4. You multiply, or you take the derivative, the integral of 2 pi x, and then you take whatever this shape is, f of x, whatever curve this is. However, in this case, we have to mix in a little bit of washer type knowledge, where instead of just me taking a regular old picture and spinning it around, I have like an upper line, which I'll call RO, and a lower line, which I'll call RI, and we're going to find out what RO minus RI is, and then dx. Okay, so that's what we're dealing with here. All right, so our OR is 7. Our OI is root x. This lower limit is A. This limit is B. And we have all the information that we need to get started. So let's get started. I'm getting a pen. We have, let's move 2 and pi out here. Keep x right there. Lower limit's 0, upper limit's 4. Parentheses RO, my upper guy is y equals 7, so we'll just do 7 minus RI is root x, close it, dx it. Okay, so this becomes 2 pi. Distributive property says 7x. Well, I still have my integral. I can't get rid of that. Not yet. 7x minus, now this is x to the first times x to the 1/2, so we'll turn that into x to the 3/2 dx. Now let's integrate that. 2 pi comes along for the ride. The integral of 7x is going to be 7 over 2x squared minus the integral. Now remember when we do this, so we'll just kind of pull this aside. We're going to have 1 over 3/2 plus 1 x to the 3/2 plus 1, right? So this will become 1 over 5/2. 1 divided by a fraction is reciprocal. So 1 over 5/2 is 2/5 x to the 5/2. Look at me just barely fitting that in there. My limits of integration are still 0 and 4. But I have what I need to start using the fundamental theorem of calculus, so I'm going to do just that. I'm going to write this out, plug in 4 for every x, so 2 pi 7/2 4 squared minus 2/5 4 to the 3/2, close it. Just making sure I didn't miss anything. Minus that guy, plug in 0. Now let's use common sense here. 2 pi times 0 minus 0 is going to be 0, so that whole thing will become 0. Let's just get rid of it. So let's do a little bit of simplifying. All right. You can use a calculator if you want to, but I don't have one on me right now. So we've got 2 pi. 4 squared is 16. 7 halves times 16 is going to be 56. So 56 minus, I guess I forgot that guy right there. 2/5 times 4 to the 3 halves. I am going to use Siri for that one. Or is it 5 halves? 4 to the 5 halves. Yeah, it's 5 halves. What's 4 to the 5 halves power?
The answer is 32.
Okay. What's 2/5 of 32?
The answer is 12.8.
So this becomes 12.8. What is 56 minus 12.8?
The answer is 43.2.
And what's 2 pi times 43.2?
It's approximately 271.4336.
Okay. So that's shells for you. Not as crazy as some of the other things that we've done that look like discs and washers and stuff like that, but also not a ton of fun either. So unless I personally find it great. It's great. So thank you. Thanks for watching. Thanks for loving this stuff. Find the volume. The base of a solid in this is the region enclosed by the semicircle y equals square root of 25 minus x squared and the x-axis. Cross sections perpendicular to the x-axis are squares, so that's important. Cross sections are squares. So this is me attempting to draw a square using this pen thingy that I'm using. It's never a good idea. So when you imagine what's going on here, a cross section is a slice, and you're cutting this down. Okay. Now, if I were to cut this solid, this volume, and literally cut it in half so that I'm looking at almost a half of a globe, what I'm looking at are squares with lengths of side lengths of 25 minus x squared and root 25 minus x squared. Now, when you're solving one of these problems, right, the volume of one of these problems is found by taking the integral of the upper limit, lower limit of the area of this particular shape. So we'll say that's called a of x dx. Now, the area for this particular shape is going to be a side squared, so the square root of 25 minus x squared, which makes life really easy because, a square and a square root cancel each other out, giving us just that right there. So what I'll do is I don't need this picture anymore. That picture's now gone now that I have my area formula. I can find the volume by taking the integral of 25 minus x squared dx. Now, what's my limits of integration? Well, if this is the formula of a circle, that tells me that this guy right there is going to be my radius squared. So in order to find the radius, I take the square root of that, which is 5. And we can see right here, if this is a circle, it goes out to 5, it goes out to -5. So this is going to be my upper limit. This is going to be my lower limit, 5 and -5. So let's do all of this. Let's get rid of you. Let's get rid of you. The integral of 25 is 25x. Can handle that one. Minus the integral of x squared is 1/3 x cubed. And my limits were 5 and -5. So now it's time for the fundamental theorem of calculus. I'm going to rewrite this guy, plug in 5, hit the minus button, rewrite that guy, plug in -5. So I have 25 times regular 5 minus 1/3 times 5 cubed, which is going to be 125. Close that. Minus 25 times negative 5 minus 1/3. It's supposed to be 25 times negative 5. Let me clean that up. Let me sneak that in there. 25, I think I said it, I just didn't write it, times negative 5 minus 1/3 of negative 5 cubed, which is negative 125. So we should know that since this guy is a perfectly symmetrical shape, that whatever number this is, once I minus this guy, it's going to be the opposite. So it's that guy plus the same exact number. So what is it? What's a third of 125? Let's ask Siri. What's a third of 125?
It's approximately 41.6666.
All right, so 125 minus 41.666.
It's 83.334.
So this is going to be 83.333 minus negative 83.333. And what is 83.333 times 2?
It's 166.666.
I don't like that. But that's the answer that we have. So the volume, according to this information right here, which is found by basically taking the area of a square, making life easy for us, is 166.6 repeating. All right, there you have it. A particle moves along a horizontal line where its velocity is given by the function below. So there you have it. Find the distance and the displacement over the interval. All right, let's understand the difference between the two. All right, displacement is the idea that we start somewhere, and let's just say I take 5 steps forward, I take 8 steps backwards. My displacement has me at -3 steps. What does that even mean? That means from where I started to where I'm finished, I am 3 steps backwards. Now, if I were to look at the same exact problem, the same exact scenario as far as distance goes, where I take 5 steps forward and 8 steps back, I don't care about like a negative position. I'm taking 13 total steps. So what we're going to do is we are going to find displacement. We're going to find distance. One's going to tell us where we are currently at the moment, and the other one's going to tell us where or how many spaces, units, whatever that we moved. So let's start with the easier one first. Let's start with displacement. Okay. Displacement is pretty simple, relatively speaking. You take the integral from where you start to where you finish of your velocity function, and that's pretty much it. Okay, nothing fancy, nothing crazy. That is the displacement. So my velocity function was 3t squared minus 22t, close that, dt. The derivative, the integral of 3t squared is t cubed minus 22t, the integral of that is 11t squared, and my limits of integration are 0 and 10. Fundamental theorem of calculus says that we write this guy out, plug in 10, so we have 10 cubed, which is 1,000, a k, if you will, and 11 times 100, which is 1,100, minus, notice I didn't write it out, plug in 0 cubed, get nothing. Plug in 0 squared, get nothing. So nothing. So we end up with negative 100, whatever. What are we talking about? Units? Nothing. It doesn't say. So we'll say that our displacement is 100 units backwards. So this is not too different from any other regular problem so far that we're used to seeing. That changes though, because if you're trying to find the distance, you don't care where you end up. You care what you've done in the positives and in the negatives. So what we do here is we set up an integral between 0 to 10 of the absolute value of our vertical or our velocity function. Okay, so that requires us doing a few things. Noticing I'm writing small because this takes a little bit of space for me. All right, so the first thing I have to do is I have to find kind of what's critical points. If I'm going to be going forwards, that tells me a distance of something. And if I'm going backwards, that tells me a distance of something too. So what I kind of need to do is find out when I'm going forward and when I'm going backwards. And the way I can find that is I find out when velocity is increasing and when velocity is decreasing. So here's my velocity function. Let's set it equal to 0 a la critical points. A la critical points. Let's factor out a t. So now we have t times 3t minus 22. According to the zero product property, t is 0. So that's one of my times. So right at the very beginning. So that makes life kind of easy. If I add 22 and divide by 3, that gives me 22 over 3 for where things change. Okay, so I'm going to create kind of like a sign chart. 22 over 3 is where the magic happens. I'm going to plug in, normally I would plug in 0, but I can't plug in 0 because technically that's a critical point. So if I plug in 1 and find out if this gives me positive or negative, that'll help. And if I plug in 10, I can actually do 10. That'll help me determine if it's increasing or decreasing. So plugging in 1 and doing some mental math, I get 3 times 1 squared minus 22 times 1 gives me a negative number. So I'm decreasing here. So between 0 seconds and 22 over 3, that's supposed to say 3. I don't know why that looked like 13. Between 0 and 22 over 3, I have, or I'm going backwards because my velocity is negative. Can I erase that little one looking thing? I'm scared. Let's go. Where? Come on. Go away. Yeah. All right. Now let's see what happens when I plug in 10, because I'm allowed to plug in 10. See what kind of number I get. 300 minus 220, positive, increasing. All right. Let's cut this down a little bit more. So in my negative section, all right, I'm going to set up an integral where I'm negative from 0 to 22 over 3, so 0 to 22 over 3 of negative VT. So by throwing a negative in front of this formula, I am allowing myself to kind of say, all right, well, I'm going to get a negative distance, but by negativing, a negative, it becomes positive. So that'll be helpful. My other inequality, which shouldn't take up too much space, is going to be from 22 thirds to 10 of regular velocity. Nothing fancy about that, dt. All right? So I'm going to have the integral between 0 and 22 over 3. Let's throw the negative out here. Of Vt is 3t squared minus 22t dt. I already know what's going to happen. I'm going to end up with this guy, so I have t negative t cubed plus 11t squared between 22 over 3 and 0. So when I do the math here, when I do, the fundamental theorem of calculus, I get negative 22 thirds cubed, whatever that is, plus 11 times 22 thirds squared, minus zeros. So 22 over 3 cubed.
It's approximately 0.
That's not at all what I wanted. What's 22 divided by 3?
It's approximately 7.333.
What's 7.333 cubed?
It's approximately 394.3165.
394.316. So we'll put 32 plus. What's 22 over 3?
It's approximately 7.
What's 7.333 squared?
It's approximately 53.77.
What's 53.772889 to the times 11?
It's approximately 591.5017.
Okay, that actually did work. So 59.1. 591.5 minus 314.32.
It's 277.18.
Okay. Lots of calculating there. This guy's going to be slightly more challenging. Slightly more challenging. Let's get a fun color. As you can see, the fun color is popped off to the side. Let's get a nice little orange in there. All right, so we already know what happens when I take the integral of VT because that happened over here. So I have t to the third minus 11t squared. Limits are 10 and 22 over 3. All right, so the nice thing about this guy right here is I know what's going to happen because I plugged 10 in over here and got negative 100. Now, when I plugged in negative 200, or when I plugged in, what was it, 22 over 3 into the negative form of this, I got positive that. So I would get minus 277.18 for this one, which is a double negative becomes a positive 177.18. So my final distance traveled is found by me taking u and adding them together, 177.18 plus 277.18.
It's 454.36.
And that's your guy. And that's distance and displacement. So on a fun scale, I'd say it's about an 11 out of 10. On a difficulty scale, same. But it's not work if you're having a great time. Am I right? Like and subscribe. Thanks for watching.